So what will help us in finding the zeros of our polynomial function will be the factored form. So our factored form is something we're going to be seeing down here in some examples, where it's just a list of the pieces multiplying that's going to equal our function. You will not have to find these factored forms. We're not going to worry about synthetic division and dividing up polynomials. These will be given to you in this form whenever you need to find zeros of a graph. So don't worry about creating these given a long string of addition of different terms. This will be provided. So our factored form. What we're going to be seeing with the factored form of a polynomial is we can have a numerical value out front. So our factored form p of x. So we can have some numerical value out front. This is going to be our value a. So let's just call that a. And then in our factored form, you'll have all of these pieces multiplying together, and there can be just so many of them. There's no limit, really. I mean, there's a limit, but we can have as many as we like. So when we're looking for the zeros of our function, what we're doing is we're solving 0 equals and then this factored form. What's nice is with our zero product property is that then we can find each of these zeros by setting each of these individual pieces equal to 0 and solving. So that's a piece that we'll be doing. There's also going to be a component where some of these might have exponents on them. So we'll want to pay attention to exponents on our factors. That's going to be called the multiplicity of a zero. So it won't really affect the value that's inside. In that, let's say, for example, this was x plus 1. Then for a 0, I would be solving x plus 1 equals 0. So I have a 0 at x equals -1. And I would want to attach whatever multiplicity is occurring to that 0. Now, why do we need to know these multiplicities? Well, that's what we're going to talk about with this graphic right here. So we have these zeros on the graph. We have a 0 at -5. We have this 0 at -2. And we have this 0 at +1. But what we can see is that there's different shapes occurring at each 0. So let's focus on this first one. With this first one, we come down, we hit that 0, and then we go back up. I think a lot of people use this term, but I know it's one that I particularly like. Call this the bounce. Like it bounces off of that 0. Now, with this 0, what's coming through is, so in our factored form, what we would be seeing as a factor is x minus 5. And then we would see our multiplicity coming through as an exponent there. Well, this looks a lot like our parabola, right? And that links directly to the exponent that's going through here. So this would have an even multiplicity. Meaning the exponent that we would see on where that 0 is coming from. So in this case, it would be an x minus 5. The sign switches between those because when we solve x minus 5 equals 0, you add 5 to both sides, and then and I even switched it, sorry. That should be at -5. So this would be x plus 5. Still switch signs, but the idea of if I solve x plus 5 equals 0, really I get x equals -5, which gives us that value there. So that's a theme that we'll have with our factored form. The numbers you see in the factored form, you switch the sign to get the value that's actually showing up on the graph. So our multiplicity for the exponent there would be even. So we'd be seeing an exponent of 2, 4, 6, could be any of those, to give us that bounce at that 0. Typically, if we're creating the function, we just go with the lowest value. So I would just use squared there. So in fact, let me write that there. An exponent of 2. So that's how the multiplicity will relate to the 0. Let's go to our next zero on our graph, which is occurring here at x equals -2. So we have x equals -2, and this is just a cross through, so it crosses there. So with this, what we'll be seeing for our 0, so again, we switch the sign. So in the factored form, it would look like a factor of x plus 2. And for the multiplicity, what we would have is just a multiplicity of 1. This is kind of our standard form of what we would do at a 0 on a graph, is typically we would just cross right through it. Our graph just continues as it normally would without any special circumstances. So this would have a multiplicity of 1. So it's like up here, the behavior around that 0 as we're zoomed in is quadratic. So it's like this bounce. It looks like x squared just around that point all zoomed in. Here, where we're zoomed in, and we could even zoom in further, it almost looks linear as we go through. So when we cross, it's kind of looking like the function x, something linear just going through. And then our last 0 here, which is occurring at +1, this looks like our cubic function. So this flattens across the 0, and it looks like our function x cubed, all zoomed in like that. So what we would have in our factored form, so again, we would switch the sign. So in factored form, we'd be seeing this x minus 1 as a factor. And then for the multiplicity, we would have an odd multiplicity. So having a value of 3, 5, 7, so on and so forth. But typically we use the smallest value. So I would use a 3 right there. So with this graph and seeing my zeros, I could actually start putting a function together here. So let's call this function p of x. Now I'm going to leave this value out front unknown. There's some number a that could be multiplying out front. Something I can notice with the long run behavior is this should be an even degree polynomial, and whatever we found for a should be positive because it's not flipped. So I kind of have that in the back of my mind here. And then what we could do is use these zeros. So I have, in the factored form, I have 3 zeros showing up. So that means I'll have 3 factors. I have a 0 at -5, so that would come through as x plus 5. I have a 0 at -2, which would show up as x plus 2, and a 0 at +1, which would show up as -1. And then what I would need to do is to adjust for the shape that's occurring at each of these. I would put exponents, which are the multiplicities. So like we said, at x plus 5, there should be an exponent of 2. At x plus 2, we would just have a 1 since it just crosses through. And at x minus 1, I would have an exponent of 3 to get that cubic shape around x, that +1 there. So that gets me very far with setting up this polynomial function and solving for it just based on the picture that we're seeing there. We could check, like I said, I would expect an even degree polynomial. So here we have x squared times x is x cubed times x cubed would be x to the 6th power. So with that, having this be a degree 6 polynomial makes sense in terms of long run behavior because of those going off to infinity on either side. Then what I would need to do in order to solve for a, which I won't do here, but we'll do this in the next video, is we would plug in a non-zero coordinate. So we couldn't plug in one of these 3 points. If we did that, it just kind of all falls apart. But something I could do is like plug in that y-intercept or plug in any other coordinate that's clear to me. And then we'd have our y value, we could plug in for x, and then it would just be a matter of solve for a. So we won't do that here, but we could find this full polynomial just from using those zeros and the multiplicities and then using a coordinate to solve for a. But let's just focus on these zeros. So what we're going to do here is determine the leading coefficient. And actually, sorry, I'm going to save that sketch of the graph to the very end. I'm going to determine the leading coefficient, find the zeros, and state their multiplicities. So let's just do that first. So I'm going to go leading coefficient. Sorry, not leading coefficient, leading term. Coefficient's just the number. I want the leading term because I want to see x and its exponent as well. Sorry about that. So I want the leading term, and I want the zeros. And for each of the zeros, I want their multiplicities. Okay, so the leading term, as we talked about with this factored form, what you're going to think about is just multiplying the pieces with x. So if I multiplied, in fact, I'll highlight them. So 2x, x, 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 and x. So numerically, I'll just have 2, and it's a positive 2. And then for x, I can just kind of count them up to determine the exponent. So I have 1, 2, 3, 4, 5. So with that leading term, I can get an idea of the long run behavior. So this is an odd power function, and our coefficient is positive. So I know for long run behavior, we're going to have this behavior coming from negative infinity, going off to positive infinity. All right, now for the zeros. So the math that goes behind this is solving 0 equals 2x times x minus 1 times x plus 2 times x plus 3 times x minus 4. So what we're doing is we're setting, since it's just a string of multiplication, we're setting each of these pieces equal to 0. So we have 2x equals 0, x minus 1 equals 0, x plus 2 equals 0, x plus 3 equals 0, and x minus 4 equals 0. So first one, divide both sides by 2. So that's just giving us x equals 0. Add 1 to both sides. Subtract 2 from both sides. Subtract 3 from both sides. Add 4 to both sides. So these are the zeros of my function. So I have the coordinate 0, 0. We have the coordinate 1, 0. Negative 2, 0. Negative 3, 0, and positive 4, 0. Sorry, I got a little messy there. So what you can notice is if you have something with x multiplying out front, or if you have x without it adding anything on, that's going to give you the origin. So that'll be 0, 0. And then like I talked about, we see this change in sign. So where we see minus 1, there's positive 1, positive 2, negative 2, positive 3, negative 3, negative 4, positive 4. So with that, you don't need to show this work each time. There are shortcuts here where you can skip over that work because really like this solving process is short. But if this helps to solve this each time, absolutely do. And in fact, in some of the next examples, this will help for when the numbers get a bit more complicated. But if you don't show this work, that's totally fine. So now for the multiplicity, what I'm going to focus on is the exponents of these factors. So here, there isn't an exponent, same thing at 1, same at 2, 3, 4. All we have here are exponents of 1. So that means for the multiplicity, we just have multiplicities of 1 for each of these, which means graphically what we're going to see is just crossing through at each of those points. So now with that, let me show you how I'm going to make a sketch of this graph. It's not going to be perfect. It's just going to be a rough sketch of what's happening, but we can get pretty detailed with just this information right here. So I'm going to do this over here. Oops. And let's see, the zeros kind of set how far I need to set my scale. So I need to see up to positive 4. So how about I'll go to 4 in either direction. 2, 3, 4. 1, 2, 3, 4. And I'm not even going to label the y-axis at all because we aren't really working with many y-coordinates here. So I'm going to leave that kind of abstract there. Now, something I like to include in my sketches here is starting with the long run behavior. I make a little note to myself that we're coming from negative infinity. So I kind of go to the far left-hand side and say, okay, from negative infinity, and then we should end up off to positive infinity. So this just kind of helps my brain know that I'm going to start drawing down here, then we're going to do a bunch of stuff, and then we should end up going off to positive infinity. And this can kind of help to double check that you have carried out the like bounces and crosses and flattens correctly. Okay, let me label the zeros. So we have 0, 0, we have 1, -2, -3, +4. And we're just crossing through each of these, so we don't need to worry about doing anything special. We're just going to go through and through. So what I'm going to do, and again, this is just a rough sketch, but we're going to come from down here, cross, turn, cross, turn, cross, 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 and this works out nicely because we are going off to positive infinity. So if you end up trapped on the wrong side of the x-axis, you might be missing a 0. You might have been supposed to bounce when you cross through. That can be a way to kind of double check. So that right there, it's not perfect, but it's a pretty good sketch of our function. And in fact, let's check it. And not great, but it has that general idea of coming from negative infinity, cross, 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 and then go back off to positive infinity. So this gives us a pretty good idea of what our function looks like based on just that information. All right, let's do this with 2 more functions. So our first one here, we want our leading term. Now, with this case where there's an exponent, what I'm going to do is think of this as x cubed, because really that piece is multiplied out 3 times. So I'm going to think of that as x cubed. So where I have x, but it's cubed, and then we'd multiply that with 2x. And then we would multiply that with x, but really there's 2 x's there, so times x squared. So for my leading term, we're going to have 2x to the 6th power. So it's positive and an even power, so my function's doing something kind of like that. Now for the zeros. So where I see -1, that would be a positive 1, 0. For 2x plus 5, if you want to do some side work with this, really we're solving 2x plus 5 equals 0. So subtract 5 from both sides, divide by 2. So this is a -5/2, 0. I'm going to go ahead and turn that into a decimal because we're going to need to graph this. So -2.50. And then where I see +6, that would be a -6, 0. Then for the multiplicity, I'm looking at the exponents. So we have an exponent of 3, we have an exponent of 1, and an exponent of 2. So we're matching up with where that 0 came from and the exponent associated with it. So like at that 2x plus 5, there was just an exponent of 1. At x plus 6, where we got the -6, 0, we have an exponent of 2. So what we're going to see here is we're going to flatten at that 1, 0. We're going to cross at -2.5, and at -6, we're going to bounce. And with that, we also have our long run behavior of this being out at positive infinity. So for a sketch, what I can do is just focus on my x values. Let's see, I'll go from -6 to +6. So for long run behavior, I'm going to have positive infinity and positive infinities, just to give you an idea of where to start and where to end. We have 1, 0, -2.5, and -6. So at -6, we're going to bounce. So I'm going to come from positive infinity, and I hit -6 first, so we're going to bounce. And then we're going to go to -2.5, which is where we cross through. And then at +1, we're going to flatten. So what I'm going to do here is this needs to turn, and then around that point, I just kind of make it look like a cubic function. And then we go off to positive infinity because we can't cross again, but that matches our long run behavior. So for our graph, again, not going to be perfect, but we can see that, okay, come down, bounce, turn, cross through, and then flatten at 1. That's pretty close. All right, just one more here. So leading term, we're going to have, and I'm just looking for my x values, so I have this -3x, I have this x that's squared, so let me write these down, -3x times x squared, then we have this 2x, oops, wrong pen, times 2x, and then just x at the end there. So this is going to be a -6, and then let's see, for x we have 1, 2, 3, 4, 5. So this is an odd power function, but negative coefficient, so it's going to be reflected. So long run behavior would look something like that. All right, for the zeros, what we would do is, if you need to do some side work, like 11 minus 3x equals 0, so we would add 3x to both sides, divide by 3, so 11/3 equals x. I'm going to go ahead and write just a decimal approximation of that so that we can graph it. So that's a 3.70. At +8, that means we would have a -8, 2x minus 21. You need to do that side work, add 21 to both sides, divide by 2. So 21 halves, and then just get a decimal estimate so that we can graph it, which would be a 10.50. And then we have x plus 12, which would mean a -12. All right, for the multiplicities, so where we got that 3.7, there's a multiplicity of 1. At x plus 8, there was a multiplicity of 2. For that 2x minus 21, multiplicity of 1, x plus 12, multiplicity of 1. So we're going to have this bounce at -8, but then everywhere else we're just going to cross right through. So for a sketch, what I'll do is, let's see, -12, so I'm just going to 4, 5, 6. I'm going to use a scale of 2. So we have zeros at about 3.7. So 2, 3.7. At -8, 2, 4, 6, 8. At 10.5, 2, 4, 6, 8, 10 and a half. And then -12, which should be here. And then at -8, we need to do something special. And if it helps, actually, you can use a color pen to just kind of show, okay, pay attention to that one. Everywhere else, we're going to cross. Now, from our long run behavior, talked about we should be coming from positive infinity and end up going off to negative infinity. So I'm going to start my graph up here. I'm going to cross, turn, and at -8, we're going to bounce. And then I just need to kind of visualize, okay, all the way over here, we're going to cross through. So I'm going to go down, turn, try that again. Down, turn, cross, and cross. And that would send us off to negative infinity. And just to check that graph there, oh boy, need to zoom out more. That's a messy one. If we play around with our axes, we should be able to see it. Let's go ahead and add some. Oh, there we go. All right, you can see we go through, bounce, turn, cross, cross, and end up off at negative infinity. So with this and our short run behavior and mixing it with our long run behavior, we can get a really good sketch of a general shape of our graph even without scaling our y-axis, just thinking about what's happening at the x-axis, and then how does our function go off to infinity on either side.